Hi, Dr. Su. Good morning. This is Bindushree Adalam. Today, I'm going to present you my project on vehicle routing problem. So, let's see the overview of this presentation. First, we'll see what's vehicle routing problem, and next we see the solving methods available for solving VRP, then implementation of this project and the geographical data, where we get the geographical data, visualization, and finally the resultant summary. So first, let's see what's VRP. Say your fleet has 100 trucks and you have to drop a delivery plan for 100 trucks and 1000 locations every day. Your plan must minimize the cost and at the same time maximize the efficiency. How do you manage that? This is exactly the question of VRP. It is one of the most difficult math problems to solve. When you have to consider multiple scenarios like the number of vehicles, vehicle capacity, time window of stores, type of goods, human resources, traffic and road conditions, etc. When you solve VRP, you can improve the vehicle utilization, which means that you can transport more goods in one go. Consequently, your fleet traveling time will be reduced, so you can save lots of logistic costs. Coming to the real world use cases of VRP, VRP is a common use case for businesses that deal with some kind of transportation, such as food delivery, package delivery, personal transportation, technician scheduling, where employees need to travel in order to perform some kind of service or task, etc. Formally, it is an optimization problem that seeks to service the number of customers with a fleet of vehicles. In real life, each use case comes with a unique set of additional constraints. Now, next, let's see the type of vehicle routing problems. First, we have the capacitated VRP, where the vehicle capacities are limited. Then we have multiple depot VRP, where the vehicles fleet is distributed over a number of depots. Then we have split delivery VRP, where the same customer is allowed to be served by different vehicles. Then we have VRP with time windows, where the customer is only able to accept the delivery during a certain time window. Then we have VRP with pickup and delivery, backhauls, etc. In this project, our main focus is on capacitated VRP. So coming to the solution methods, basically there are two important approaches for solving vehicle routing problem. The first one is exact approach. The goal of exact approach is to design algorithms that can find the optimal solution most efficiently. They are rarely used for practical applications due to the difficulty of VRP. It takes them unreasonably long to find solution for even moderate sized problems, so they are slow. Examples of exact approach algorithms are branch and bound algorithms. Then we have the heuristic approach. Heuristic approaches are designed to provide solutions quickly by trading optimality for speed. So while they only produce an approximation of the optimal solution, you can get something in hand so that you can use them to solve uh, and get at hand. You can solve the problem at hand, and finally, you get it in a reasonably short amount of time. Then we have the meta heuristics. Meta heuristics is nothing but the subset of the heuristic approach. These are methods for controlling the basic heuristic algorithm more efficiently. One of the characteristics is that they are not problem specific. This is the key reason why meta heuristic approach is taken. And examples of meta heuristics are simulated annealing, local search, taboo search, and late acceptance, etc. So in this project, we are using the local search algorithm. So let's see what the local search algorithm does. It starts from an initial solution and evolves that single solution into a mostly better and better solution. It uses a single search path of solutions, not a search tree. Since the local search needs to start from an initialized solution, it is usually required to configure a construction heuristic phase before it. So it's all basically in 4 steps. The first step, the local search tries a number of moves on the current solution and picks the best accepted move as the step. Then a move selector which selects the possible moves of the current solution. Then we have the acceptor, which filters out the unacceptable moves. Then we have forager, which gathers accepted moves and picks the next step from them. The solver remembers the best solution it has encountered through the entire search path. Each time the current solution is better than the last best solution, the current solution is cloned and referenced as the new best solution. Then here, now let's see the different neighborhood operations we'll be performing in this project. First, the swap procedure. The swap procedure takes into account two different nodes and swaps these nodes. This operation is easiest and it is used in many problems which are solved using local search. So here you can see that the nodes 4 and 5, after swapping them, you can see here they have two different routes. So basically you are avoiding this cross path over here. So the main advantage of this operation here is it allows us to get rid of between route X operations, and it is a both in route and between route operation. Coming to the next one, reverse edge procedure. Reverse edge procedure takes two different nodes which have a common route and reverses the subroute, including both the nodes. In heuristic solutions, we usually see X crossings, which can be fixed by applying this operation without violating the capacity constraints. So here you can see the edges are 6, 5, 4, and after reversing it becomes 4, 5, 6. So here you're avoiding this cross path. It is an in-route operation. The next one, we have delete and insert procedure. It takes a node, deletes it, and then it inserts it in the best possible place among the route. It allows us to change the number of customers in the route and decrease the number of routes. It is both in route and between route operation. Here you can see the node 5 and 4. Here it's deleting and inserting here. The fifth node, it's deleting in this path, from this path, and it's inserting into this path. So here again, you're avoiding this crossing over here. Next, coming to the implementation of meta heuristics. Here we build an API using heuristic design in Java. Then we implement the local search algorithm, code scoring function as part of the API. And then we combine the optimization algorithm, that is meta heuristics, with score calculation by a rule engine called rules. And we use Swing UI for user interface. Then coming to the VRP scoring function, we're writing the scoring function that allows to compare the quality of different solutions discovered by the search algorithm. We finalize the solution score by a number representing the cost of each route traversed by a vehicle. It doesn't really matter whether we optimize for the fastest or shortest route. In both cases, you have to get the number based on the length and type of route connection between the points in the entire route. To search the solution space efficiently, it has to calculate the score quickly. So this means that you should evaluate any IO operation during the score calculation, especially accessing files on the system or API services over the network. You have to calculate the complete distance metrics for all locations which are part of the problem and keep that metrics in memory while the application is running and determine the final and optimal solution as final result. Then coming to OpenStreetMap, there's a project called OpenStreetMap which contains geographical data about the whole world. Data is contributed and maintained by the community and it is open. This project gives us the travel time between any two given points on a map. To extract the exact type of information that we need from OpenStreetMap data, specifically, we need to find route connections between points of interest and the time it takes to traverse such connections using selected type of vehicle. And this is the link where you can find the OpenStreetMap data. Then here in this project, we also add an important feature called real-time planning, in which we can provide new information about the problem while the server is running. It still takes that into account and gives the best solution according to that. When there is a dynamic change in inputs, it will still take that into account and give the best solution according to that. Then coming to the VRP mechanism, this is the basic VRP mechanism we'll be using in this project. First, we have the depot over here. Each node, this is the starting point of the problem. And then we have nodes. Each node represents the demand locations, that is the customer locations. It must have a demand greater than 0. Then we have the routes over here. The paths, routes are nothing but the paths that the vehicle should follow to get to the demand locations. Then we have the arcs. Each arc represents a route from one node to another node. Then while designing VRP, you should keep in mind the hard and soft constraints. Coming to the hard constraints, we have the vehicle capacity. A vehicle cannot carry more items than its capacity. Then we have time windows. This is in the case of capacitated VRP with time windows. We have travel time, customer service duration, customer ready time, customer due time. You have to always make sure that the hard constraints must not be broken. Then coming to the soft constraints, we have total distance. We have to minimize the total distance driven by all the vehicles so that you can save the fuel. And soft constraints also should not be broken if it can be avoided. Hard constraints are weighted against other hard constraints. Soft constraints are weighted too against other soft constraints. Hard constraints always outweigh soft constraints regardless of their respective weights. Then coming to the result, let's see the project and run it in Eclipse. So this is my project. So let's run this. So these are the input files over here. So I'm selecting one of the input file, and here you can see the depot. Each node over here represents the customer location, and the number over this node represents the amount or capacity to be delivered to that particular customer. So here we have 32 customers and 6 vehicles. Now when I click on solve, you can see initially the distance is 1079. Gradually it's decreasing as the algorithm finds the best route. And finally you can see the distance as 743.44. Here, these are the vehicles, each has a capacity of 100, and the capacity fulfilled here is used is 98, and so forth. So as I told you earlier that I have implemented an important feature called real-time planning. So now the program is running. Even though it's running, you can add more customers here and it will still take that into account and give the best solution. So you can add any customer by right-clicking anywhere in the screen. So I'm adding here. So you can observe that it's still taking that into account and giving the best solution. And let's see the worst case scenario. Now, there are 6 vehicles in total, and each vehicle has a capacity of 100. So the total capacity is 600. So now let's see what happens when we increase the load to be delivered to the customers beyond the vehicle capacity, that is 600. So I'm adding more customers and more load here. You can see it's taking everything into account and running. Now you can see that the limit has increased beyond the vehicle capacity, and hence it is highlighted in red color here. And you can also observe that the solution is not feasible since it has exceeded the limit of the vehicles and hard constraints have been broken. So let me stop this here. And here you can see that the vehicle capacity, which is the hard constraint, has been broken. So the solution here is not feasible. So this is my project. And you can also save the solution for future purposes if you require by clicking on save as and selecting, and you can save it in XML format. Now let's go back to the presentation. Here I have placed the screenshots of the same. This is before running the program. This is before solving. You can see the distance. After solving, the distance has reduced. And finally, this is the worst case scenario. If the capacity is increased, then the solution is not feasible. Coming to the summary, uh, so VRP is very difficult. So we have taken the meta heuristic approach here along with the local search algorithm. And uh, here a rule engine such as rules, which is used in this project, is great for calculating the score of a solution of a planning problem. It makes it easy and scalable to add additional soft or hard constraints. It does incremental score calculation without any extra code. This is a huge performance and scalability gain. Constraint streams and rule score calculation give this huge scalability gain without forcing you to write a complicated incremental score calculation algorithm. Also, the time complexity of recursive based approach based algorithms is big of 2 power n, whereas the time complexity for the meta heuristic approach which is used in this project is big of n. You can see that it is far better than the traditional method. So this is my project on VRP. Hope you like it. Thank you.